Welcome, and we're going to talk about the Hungarian algorithm today. The input to the Hungarian algorithm is a weight matrix. The weight matrix is corresponding to a vertex set of x1, 2, all the way through xn, and y1, y2, all the way through yn. This is corresponding to a bipartite graph where each bipartite set has n vertices. So we have the x side and the y side. And inside the matrix, the entry wij is the weight of the edge between xi and yj. Right, we're assuming we have all the edges in our bipartite graph because if you don't want that edge, you may as well make the weight be 0. And our goal is to find a maximum weight perfect matching, which is equivalent to finding a maximum weight transversal of this matrix. While we run our algorithm, we're going to hold on to a data structure called the excess matrix, and we're also going to store two weighted vertex covers. We're going to have u1, 2, all the way through un, and v1, v2, all the way through vn. Okay? We're going to think about these as being weights on the vertices of the x's, and the v's are weights on the vertices of the y's. And the condition that we want to ensure throughout the entire algorithm is that for every pair ij, the weight on the edge ij is bounded above by the weight of the cover on xi and on yj. All right? So this is what we are going to be verifying the entire time. And we're going to try to reduce the total sum of the u's and the v's as we go along. And one helpful structure is the excess matrix. The excess on the edge ij is the amount that the edge is covered, which is ui plus vj minus wij. Right? Because this constraint always holds, the excess will always be non-negative, okay? Which means it's 0 or larger. And we're going to use this matrix and an interesting data structure on the zeros in order to improve our algorithm. Okay? Now, when we initialize, we can make all the v's be 0 and the u's be the maximum values across that row. And that's going to be a feasible vertex cover because this constraints will always hold. Okay? So the u's will be the maximum across the rows, the v's are all 0. And as we continue, we will increase the values of the v's while decreasing the values of the u's. And eventually we will terminate where I have a vertex cover and a perfect matching of the same weight. When we perform an iteration, the first thing we're going to do is we're going to find the equality subgraph, which is essentially, I'm going to look at the excess matrix and see if there's a 0 at any position, I will put that edge in my subgraph. Then I'll look for a maximum matching M in this graph and a minimum vertex cover, Q, such that Q and M have the same size. We can do this using our augmenting paths algorithm. If this matching is a perfect matching, then we actually have a perfect matching where the excess is 0 on every single edge of the matching, which means that this vertex cover has the same weight as that matching in the original weights. Therefore, M and this vertex cover are optimal, so output both. Okay? And by this notation, I mean the vector of all u values and the vector of all v values. Otherwise, we will compute a few extra details. For instance, we'll look at our vertex cover Q and look at all the vertices in X and Q, and those be vertices in R. And then let T be the set of vertices that are in Q and Y. And then we'll look for this epsilon value, which is going to be the minimum excess that's outside of R and T. So I'm looking for the excess ij, so entries of this matrix, such that xi is not in R and yj is not in T. We can find this by using some notation to denote what is in R and T. We can use markers on our excess matrix. To the right, we will mark off rows which are in R. Okay? This means that the entry of this vertex would be in the set R. And then also a column we'll mark below with a T if that Y vertex is in T. Right? And that what we essentially are doing is we're looking for entries of the matrix which are not in the columns marked T or in the rows marked R. And that's what our value epsilon will be. And then finally, we can finish our iteration by updating our values of u and v. So I will decrease the value ui by epsilon if the vertex xi is not in R, which means it's not in the vertex cover. I will increase vj by epsilon if yj is in T, is in the vertex cover. Okay, it's very important that you get these two directions correct. I will remove epsilon from ui if that row is not in the vertex cover. I will increase a column cover value by epsilon if that column is in the cover. So essentially what's happening is if I mark out the columns and the rows which are in my vertex cover, I will be increasing these values at the top of these columns by epsilon. And over here, I will decrease the rows which are not in R by epsilon. So what happens is that these entries here that are in neither the R or T, all of those entries will go down by epsilon because they're going down by, when I look at the new excess matrix, these entries will go down by epsilon. The parts that are in both in T but not R, those numbers will stay the same because I'm reducing this by epsilon but increasing this by epsilon. And the numbers that are in both, they'll actually increase by epsilon because I'm not changing the row cover, but I'm increasing the T cover. Okay? And so that's how you know how to update the excess matrix. Of course, you can update it straight up from using the U's and V values that you've recently updated. Now it's time to look at an example so we can really see this in action.